Swayam Prabha. Digital India. Educated India.
Welcome to lecture 5 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Multiple Linear Model and Least Squares Estimation. In the previous lecture, we discussed the simple linear regression model, which establishes a linear relationship between a dependent and an independent variable. So, basically we assume that the variations in y are due to a variable x, a single variable x, or you want to explain the changes in y on the basis of changes in a single variable x. Now, often in many applications, you may have a set of independent or explanatory variables affecting the dependent variable y. So, instead of a single explanatory variable, you have a set of explanatory variables. So, obviously, in those cases, to improve the predictive power of the model, you may like to establish a multiple relationship or a joint relationship between y and the set of all the explanatory variables. So, in those cases we use the multiple regression. You may also be interested in the variables which are actually important for explaining the variations in y, the variables which are not so important for explaining the variation in y. So, you may like to identify those variables. So, now in this lecture we consider the case when you have a set of explanatory variables and you want to model the variations in y on the basis of that set of explanatory variables. So, we consider the multiple linear model for this purpose. We also discuss the method of least squares for estimating the parameters of the model. Then you may also be interested in estimating the variance of the error term. So, we will obtain an unbiased estimator for the variance also. So, now we come to the multiple linear regression model. So, in simple linear regression model, you have a dependent variable and one independent variable. In multiple regression model, your study of dependent variable depends on more than one explanatory or independent variables. So, you have a set of explanatory variables affecting your dependent variable. Then your focus of attention is, or you are interested in, what is causing variation in dependent variable, or which variables are mainly responsible for variation in dependent variable. Of course, you have a set of variables which you believe that may affect the variation in dependent variable, but some of those variables may not be so important. So, you are interested in identifying the variables which are mainly responsible for variation in the dependent variable. Here are some examples. Say scientists might be interested in observing the effect of different amounts of fertilizer, different levels of irrigation and different types of soil on crop yield. So, instead of just a single variable like different amounts of fertilizer or different levels of irrigation affecting the crop yield, here you have more than one variables. You have a set of variables which may affect the crop yield. So, crop yield is your dependent variable, and explanatory variables are different, say, amount of fertilizer or levels of irrigation or different types of soil. Then selling price of a house may depend upon the location of the house area, whether the house has sea facing or not, the number of bedrooms the house has, the number of bathrooms the house has, or how old the house is, etc. Again, you have a set of variables which may affect the selling price of a house. Now, some of these variables may be more important in explaining the selling price of the house, and some of these variables may not be so important. So, again we denote the dependent variable by y. So, y is the dependent variable, then you have k independent or explanatory variables x1, x2, xk. And we assume that expected value of y is equal to x1 beta 1 plus x2 beta 2 plus so on plus xk beta k. So, again we assume that there exists a linear relationship between y or the expected value of y and x1, x2, xk, or you can write the model as y equal to x1 beta 1 plus x2 beta 2 so on plus xk beta k plus u, where u is your disturbance or error term. Usually we take x1 equal to 1 to allow for the intercept term. Say, remember, in two variables case we considered the model y equal to beta 1 plus beta 2 x. So, basically we took x1 equal to 1 and x2 equal to x, and x1 equal to 1 means you get this intercept term here. So, we take x1 equal to 1 to allow for the intercept term. U is the difference between actual value of dependent variable and its expected value, means y minus expectation of y gives you u, or this is the predicted value of y using the regression, and this is the actual value of y. So, the difference between actual value and predicted value of y gives you the disturbance term or error term u. So, u is called the random error or disturbance term, and it is u which makes your model stochastic. Beta 1, beta 2, beta k are the unknown regression coefficients. These are unknown constants, and ultimately you have to estimate these unknown constants or the unknown regression coefficients or unknown parameters of the model on the basis of observed data. Now, if we differentiate expected value of y with respect to xj partially, say for example, if we differentiate expected value of y with respect to x2, then we obtain beta 2. If we differentiate expected value of y partially with respect to xk, then we get beta k. So, actually beta j gives you rate of change in y with respect to xj, or you can say if we change xj by 1 unit, say xj by xj to xj plus 1, then expected value of y changes by amount beta j, provided all other variables remain constant. Then we can also give interpretation of these regression coefficients as elasticity. In economics and engineering applications, elasticity is measured as a percentage change or percentage response. So, for instance, the price elasticity of demand of a commodity is the percentage change in quantity of demand resulting from unit change in price. So, for example, suppose 10% increase in price of petroleum results in 2% decrease in demand. Then the price elasticity is 0.02 divided by 0.10, or it is equal to 0.2, and then the corresponding regression coefficient is minus 0.2. Or If 20% increase in price of mango results in 40% decrease in its demand, then the price elasticity is 0.4 divided by 0.2, which is equal to 2, and then the corresponding regression coefficient is minus 2.0. Now, your next objective is to obtain estimators of unknown parameters. So, you want to estimate the regression coefficients beta 1, beta 2, so on beta k. So, then we take observations. So, suppose you take n observations. So, these are the sample numbers 1 to n, and corresponding to each sample get observations on dependent variables, say y1. y1 is corresponding to k independent variables x11, x12, so on x1 k. Then the second observation y2 is corresponding to x21, x22, so on x2 k, and so on. yn is corresponding to xn1, xn2, so on xn k. So, actually xij is the ith observation on the jth independent variable. I varies from 1 to n and j varies from 1 to k. So, ultimately you have k variables on each k independent variables. On each independent variable you have n observations, and corresponding to each set of observation on independent variables you have this observation on dependent variable. Now, we take certain assumptions which are required for developing the least square theory for estimating the parameters of the model. So, the first assumption is that the following linear relationship exists between y and x's. So, corresponding to the first observation, y1 is equal to x11 beta 1 plus x12 beta 2 plus so on plus x1 k beta k plus u1. u1 is the random disturbance term corresponding to the first observation. Then corresponding to the second observation, y2 is equal to x21 beta 1 plus x22 beta 2 plus so on plus x2 k beta k plus u2, and so on. Corresponding to the nth observation, you have yn equal to xn1 beta 1 plus xn2 beta 2 plus so on plus xn k beta k plus un. Then u1, u2, un are the random disturbances or error terms. It becomes more convenient to write the model or derive the least square estimators for the parameters if we use the matrix notations. So, we introduce the matrix notations. We take n cross 1 vector y equal to the column vector y1, y2, yn. So, actually y is n cross 1 vector of observations on the dependent variable. Then we take n cross 1 vector xj as x1j, x2j, so on xnj. So, actually xj is n cross 1 vector of observations on the jth explanatory variable or jth independent variable. Then this beta is k cross 1 vector with elements beta 1, beta 2, so on beta k. So, beta is k cross 1 vector of regression coefficients beta 1, beta 2, beta k. Then this u is again n cross 1 vector with elements u1, u2, un, or you can say u is n cross 1 vector of random disturbances. Then we can write the model 1 in the form y equal to x1 beta 1 plus x2 beta 2 so on plus xk beta k plus u. So, we can write the model 1 in this form using these vector notations. Next, we introduce this matrix X, which has different columns x1, x2, so on xk. So, actually this X is n cross k matrix, all in terms of different elements xij's. You can write X as say x11, x12, so on x1k, x21, x22, x2k, so on xn1, xn2, so on xnk. So, this X is n cross k matrix of observations on k explanatory variables. Then in matrix notations, you can further write the model 1 as y equal to x beta plus u. So, this is the final form of the model which we are going to use for different purposes, for the estimation purpose, etc. And then as I mentioned earlier, the first column of X consists of all elements equal to 1 to allow for the intercept term. That is, we take x11 equal to 1, x21 equal to 1, so on xn1 equal to 1. So, that the matrix X is, you get first column with all elements equal to 1, and then you have x12, so on x1k, x22, x2k, so on xn2, so on xnk. This n cross k matrix. So, usually we take the first column of X as 1 1 1. Then the second assumption is expected value of u I is equal to 0 for all I equal to 1 to n. Again, sometimes your error is positive, sometimes it is negative, but on average we assume that it is 0 or its expected value is 0. So, if we take the expectation of u means expectation of u1, u2, un. So, expectation of this random vector means expectation of u1, expectation of u2, so on expectation of un, and expectation of ui is equal to 0 for all I equal to 1 to n. So, expectation of u is a vector with elements 0 0, so on 0. So, this 0 is actually n cross 1 vector with all elements 0. Third assumption is expectation of ui square is equal to sigma square u for all I equal to 1 to n. So, all the ui's have the same variance sigma square u, and expectation of ui dash is equal to 0 for all I not equal to I dash. If I is not equal to I dash, then the expectation of ui dash is equal to 0. So, this assumption implies that all the ui's have same variance sigma square u, and this assumption implies that ui's are pairwise uncorrelated with each other. All the ui's have same variance means ui's are homoscedastic. If all the ui's have same variance, then these ui's are called homoscedastic, and this assumption implies that all the ui's are uncorrelated with each other. Now, remember that u transpose, u is n cross 1 vector and this u transpose is 1 cross n, and then you can easily obtain u transpose, which is equal to u1 square, u1 u2, u1 un, u2 u1, u2 square, u2 un, and so on, un u1, un u2 un square. And if we take expectation of u transpose, then what we get? In the diagonal we obtain expectation of u1 square, expectation of u2 square, so on, expectation of un square. So, sigma square u, and the off diagonal elements have expectation 0 because of this assumption. So, you obtain sigma square u 0 0 0 sigma square u and so on. And then you can write it as sigma square u times I n. So, expectation of u transpose is equal to sigma square u I n. So, you can say that the mean vector of u is 0 and the variance covariance matrix of u is sigma square u times I n. So, I write expectation here also. The next assumption 4 is rank of x, which is denoted by rho x is equal to k. K is the number of columns of x, and we also assume that k is less than or equal to n. Or you can say x1, x2, xk are linearly independent. Different columns of x are linearly independent. And you may note that if rank of x is less than k, then of course, sum of the linear combinations of beta 1, beta 2, so on beta k, say lambda 1, beta 1, so on plus lambda k, beta k, and you can write it equal to lambda transpose beta, can be estimated unbiasedly, but all such linear combinations cannot be estimated unbiasedly. So, this is the problem with the linearly dependent columns of x. If the columns of x are not linearly independent, then you cannot unbiasedly estimate all such linear combinations. Of course, you can estimate some of the linear combinations like lambda transpose beta unbiasedly, but you cannot estimate all the linear combinations. So, we assume that the matrix X is of full column rank. The next assumption 5 is X is non-stochastic matrix, or even if X is stochastic, it is uncorrelated with U. That is, expectation of X transpose U is equal to 0, or you can say expectation of U given X is equal to 0. U is uncorrelated with X. Now, if you take expectation of Y, then using these two assumptions 2 and 5, we obtain expectation of Y equal to X beta. Your model is Y equal to X beta plus U. And if you take expectation of Y, it is equal to expectation of X beta, which is equal to X beta, because you are taking X as non-stochastic, and then you have expectation of U, which is 0. Or corresponding to the ith component, you have expectation of yi is equal to xi1 beta 1 plus xi2 beta 2, so on, plus xik beta k for all I equal to 1 to n. So, for all the observations, n observations, or for all I equal to 1 to n, you get expectation of yi equal to this. Next assumption 6 is, sometimes we assume that u follows a normal distribution. For obtaining the least square estimators, you do not require this assumption of normality. But sometimes when we apply maximum likelihood procedure for estimating the parameters, or when we want to test certain hypothesis, then we require the assumption of normality. And then we may combine these assumptions 2, 3 and 6 as u follows a normal distribution, and since expectation of u is 0, so it has mean vector 0. Variance covariance matrix of u is equal to sigma square u I n. Remember that our least square procedure is based on all these assumptions, but sometimes these assumptions may be violated. So, then we require some alternative procedure for estimating the parameters. Just for example, if we take this assumption of homoscedasticity. Now, suppose y is the travel expenditure of a family and x is the income of the family. Then normally the families having higher income, or the families belonging to higher income group, have on average those families have higher travel expenditure. Not only that, but if you compare the variability, then in comparison to the families of lower income group, the travel expenditure of families of higher income group have more variability also. So, this assumption may not be satisfied, the assumption of homoscedasticity. And sometimes when you have time series data, your different observations may have some kind of correlation also. Those cases, the assumption of uncorrelated errors or uncorrelated observations may not be satisfied. So, then you require some alternative estimation procedure. But presently we assume that all these assumptions are satisfied to develop the least square procedure for estimating the parameters of the model. And sometimes we also take this assumption 7. So, particularly when we are interested in studying the asymptotic properties such as consistency of the estimator of beta, we assume that the probability limit of 1 upon n x transpose x as n tends to infinity is q, and this probability limit exists, and this q is a non-stochastic and positive definite matrix with finite elements. So, in probability as n tends to infinity, 1 upon n x transpose x tends to a non-stochastic positive definite matrix with finite elements q. This assumption we require for proving the consistency of least square estimators. Now, we derive the ordinary least squares estimator of beta, and suppose we denote the estimator of beta by b. B is k cross 1 vector with elements b1, b2, bk. In the method of least squares, we obtain b by minimizing the residual sum of squares s equal to summation I equal to 1 to n yi minus xi1 b1 minus xi2 b2 so on minus xik bk whole square. And then in matrix notations you can write this sum of squares of residuals as y minus xb transpose y minus xb. So, basically to obtain b, we minimize this quantity and the resulting estimator is called the ordinary least squares estimator or OLS estimator of beta. Then we are assuming that x is a full column rank. So, when x is a full column rank, the OLS estimator of beta is given by B equal to x transpose x inverse x transpose y. To prove this result, we write S as, say, S is equal to y minus x b transpose y minus x b. So, you can write it as y transpose y minus b transpose x transpose y, then you have minus y transpose x b plus b transpose x b. Then b transpose x transpose y is equal to y transpose x b, because ultimately y transpose x b or b transpose x transpose y, these are the scalars, and b transpose x transpose y is the transpose of y transpose x b, and transpose of a scalar is the same scalar. So, these two are same. So, we can write S as y transpose y minus twice b transpose x transpose y plus b transpose x b. Now, we can write x as, say, we take b transpose x b minus twice b transpose x. So, basically what we are doing, we are taking x transpose x inverse here at this place, x transpose y, plus then we add y transpose x transpose x inverse x transpose y here, and we subtract y transpose x transpose x inverse x transpose y here, and then you have plus y transpose y here. Now, if we combine these three terms, then combining these three terms we obtain b minus x transpose x inverse x transpose y transpose x b minus x transpose x inverse x transpose y. You can easily verify it, because the first term is a b transpose x transpose x b, you get this, minus 2 times b transpose x transpose x transpose x inverse x transpose y, you get this term, plus you get minus this, so you get plus sign, and then you take transpose of this quantity y transpose x transpose x inverse x transpose x inverse x transpose y, this term, and then we write v equal to y transpose y minus y transpose x transpose x inverse x transpose y. So, we write v equal to this, or you can also write v as y transpose m y, where m is this matrix I n minus x transpose x inverse x transpose. So, you simply substitute the value of y m here, then you get y transpose y minus this term. So, ultimately this v does not involve b. So, S is minimum when the term b minus x transpose x inverse x transpose y x transpose x b minus x transpose x inverse x transpose y is minimum. So, ultimately you have to minimize this term. Now, remember that this matrix x transpose x can be shown as positive definite. Actually, if you take any p cross 1 vector C, then C transpose x C can be written as D transpose D, where D is equal to X C. And notice that different columns of X are linearly independent. So, for any non-null vector C, D is also non-null, because different columns of X are linearly independent. And since D is non-null, D transpose D is greater than 0. This is equal to 0 if and only if C is equal to 0. So, X transpose X is positive definite. So, the minimum value of this equation 4 is 0. It can't be negative because X transpose X is positive definite matrix, and it attains the value 0 when B is equal to X transpose X inverse X transpose Y. Alternatively, we can derive the least square estimator or OLS estimator by the method of differentiation. So, we write S equal to Y transpose Y minus 2 B transpose X transpose Y plus B transpose X transpose X B, and then we partially differentiate S with respect to B. So, del S by del B is equal to the derivative of first term becomes 0, the derivative of second term is minus 2 times X transpose Y plus the derivative of third term is 2 times X transpose X B, and then we write it equal to 0. Then this gives you X transpose X B equal to X transpose Y, and then rank of X transpose X is equal to rank of X, which is K. Order of X transpose X is K by K. So, X transpose X is a non-singular matrix. So, from here you can write B equal to X transpose X inverse X transpose Y. Further, if you take the second derivative, then del 2S by del B transpose is equal to 2 times X transpose X. Again, X transpose X is a positive definite matrix. So, this implies that S is minimum for B equal to X transpose X inverse X transpose Y, and this B is the ordinary least square estimator of beta. Now, we prove that the OLS estimator of B is an unbiased estimator of beta. For this purpose, in this expression for B, we write Y equal to X beta plus U. So, you get X transpose X inverse X transpose X beta, which is equal to beta, because X transpose X inverse X transpose X is identity matrix, plus X transpose X inverse X transpose U. Then we take expectation of B. We also observe that expectation of X transpose X inverse X transpose U is equal to 0, because in assumption 5 we have assumed that X is either non-stochastic, or even if it is stochastic, X is uncorrelated with U. So, expectation of X transpose U is 0. So, expectation of this term becomes 0. So, expectation of B is equal to beta for all beta. So, this gives the result that B is an unbiased estimator of beta. Then for B equal to X transpose X inverse X transpose Y, obviously the error sum of squares is V, which is equal to E transpose E, or E is equal to Y minus X B. We simply replace beta by B. Or you also notice that for B equal to X transpose X inverse X transpose Y, this term vanishes. So, ultimately you get this term only V, and then you can write it as Y transpose M Y, where M we have already defined earlier. M is actually equal to, now we obtain an estimator of sigma square U. So, we write V equal to Y minus X B transpose Y minus X B, or this is equal to Y transpose M Y. Or we also observe that V is equal to Y transpose Y minus B transpose X B, or you can also write V as Y transpose Y minus B transpose X transpose Y. So, these are the alternative expressions for V. Any of these expressions you can use. Then we will prove the result that an unbiased estimator of sigma square U is S square equal to V upon N minus K. Now, the OLS residual vector is E equal to Y minus X B, and you write it equal to M Y, because ultimately Y minus X B is equal to Y minus X transpose X inverse X transpose Y. So, this is equal to M Y. Also notice that M is a symmetric idempotent matrix, and Mx is equal to 0. You can easily verify it. Mx is equal to X minus X transpose X inverse X transpose X. So, this is equal to 0. So, you can write E equal to My, and then you write Y equal to X beta plus U, Mx is 0. So, this is equal to Mu. E transpose E is equal to U transpose Mu, because M is symmetric as well as idempotent. We are writing it equal to V. For the trace of M is equal to N minus K. Then if we take expectation of V, which is equal to expectation of U transpose Mu, and then we write U transpose Mu equal to trace of U transpose, and then we take expectation, or you can also write it as trace of U transpose M. Both are same. And then we take expectation of U transpose is sigma square In, and we take sigma square U outside. So, finally, you obtain expectation of M is equal to M. So, you obtain trace of M here, and trace of M is equal to N minus K. So, expected value of V is sigma square U N minus K. Or if you write, you are writing S square equal to V upon N minus K. So, expectation of S square is equal to sigma square U. So, S square gives you an unbiased estimator of sigma square U. In the next result 5.4, we obtain the variance covariance matrix of the OLS estimator B. So, the expression for the variance covariance matrix of B is given by expectation of B minus beta transpose is equal to sigma square U X transpose X inverse. To derive this expression, we write B equal to, say, X transpose X inverse X transpose Y, and then we replace this Y by X beta plus U. So, the first term becomes beta plus X transpose X inverse X transpose U. So, from here we obtain B minus beta equal to X transpose X inverse X transpose U. Then B minus beta transpose is equal to X transpose X inverse X transpose U, and then we take transpose of this, means U transpose of X transpose is X, and then transpose of X transpose X inverse is X transpose X inverse. Then taking expectation, we obtain expectation of B minus beta transpose equal to X transpose X inverse, X transpose expectation of U transpose X, X transpose X inverse. Then expectation of U transpose is equal to sigma square U I n. So, you get X transpose X inverse, X transpose sigma square U I n X, X transpose X inverse. So, sigma square U you can take outside, then you obtain X transpose X inverse, X transpose X, X transpose X inverse. And since X transpose X, X transpose X inverse is identity matrix, so finally you obtain this expression for the variance covariance matrix of B, sigma square U X transpose X inverse. The diagonal elements of this matrix will give you the variances of different components of B, whereas the off diagonal elements will give you the covariances between different components of B. Now, this B is a linear function of Y. Actually, B is equal to X transpose X inverse X transpose Y. This is your B, and you can write B as CY, where C is this matrix. So, different components of B are the linear function of different components of Y. So, in this sense you can say that B is a linear function of Y. So, B is called a linear unbiased estimator of beta. So, in the next lecture we will show that in the class of all linear unbiased estimator, B is the best linear unbiased estimator in the sense that it has minimum variance. So, in several applications we observe that it is not a single variable, but a set of multiple variables are responsible for the variation in dependent variable Y. And to model such situations, we can use a multiple regression model or multiple linear regression model. In multiple linear regression model, we have a set of explanatory variables, and then we form a linear relationship between the dependent variable or the variable to be explained by the model and the set of explanatory variables. Then we have also discussed the method of least squares for estimating the regression parameters as well as the variance of disturbances for the model. Of course, to derive the least square estimator or to prove different optimality properties of the least square estimator, we require certain assumptions for the model. So, we have discussed all those assumptions. Of course, in subsequent lectures we will consider the situations when those assumptions are not satisfied and how to handle the situations when those assumptions are not satisfied. So, here I am going to stop. Thank you.
Hi, I'm Chitwan Lalji, a PhD student of Health Economics under the supervision of Dr. Debyan Pakrashi from the Department of Humanities and Social Sciences, IIT Kanpur. In one of my essays, I'm interested in understanding the relationship between consumption of fruits and vegetables and various health indicators. Health indicators, both subjective and objective health indicators like mental health, self-assessed health, various measures of blood pressure and various measures of cholesterol. Measures of blood pressure like systolic and diastolic BP, you have your incidence of high BP, MAP and incidence of high MAP. And as far as cholesterol is concerned, I have tried to concentrate more on total cholesterol, good cholesterol and incidence of high cholesterol. Now before I go on to what have been my major contributions and various policy implications, I would like to briefly tell you about the policy initiatives of WHO and various countries. The WHO, that is the World Health Organization, it started with a campaign of 5 a day. That is, you should have 5 portions of fruits and vegetables per day. That would be approximately, you could say, 400 grams of fruits and vegetables. Now, a portion, before we go further, I'll just tell you what exactly is a portion. One portion is equivalent to a medium-sized apple, or one small glass of fruit juice, which is approximately 150 milliliters, and maybe 3 teaspoons of vegetables. So, the WHO went with a 5 a day campaign, which was further taken up by various countries. Countries like UK, Netherlands, Germany, Norway, they adopted the 5 a day policy, while some went for expansionary dietary policies like France, Australia, Canada, Denmark. So, for example, Australia, it went for 2+5 policy, in which it said that you should consume 2 portions of fruits and 5 portions of vegetables per day. And USA went for a policy of fruits and vegetables more matters. That is, you must consume more and more fruits and vegetables. Now, irrespective of these expansionary dietary policies and dietary propagations, it has been found that only 28% of women and 25% of men, they actually meet the recommended dietary norms of 5 a day portion. So, the major contribution of my work is firstly to find an association between fruits and vegetables, whether there exists a relationship between fruits and vegetables and health indicators, and if they exist, whether due to heterogeneity in the data. So, I will be doing it according to age, by gender and by your weight. So, apart from that, I will go for policy recommendations, in which I am basically studying how much fruits and vegetables matter. Apart from that, which type matters more. So, for that I have taken data from the Health Survey of England. Health Survey of England is an annual survey which takes data, which conducts information regularly on demographic and socioeconomic characteristics. You have your lifestyle behaviors like an individual smokes or doesn't smoke, alcohol consumption, you have your sedentary and physical activities, and you have various health indicators also which have been collected. Before I go on to what exactly is my research, I would like to concentrate more on fruits and vegetables, like what kind of questions were asked in the survey. Questions like, what kind of fresh fruit do you eat? Did you eat any dried fruit yesterday? Don't count dried fruits in cereals, cakes. Apart from that, for vegetables, they asked how many tablespoons of vegetables did you eat yesterday. So, approximately after this whole survey was conducted, data was converted into portions of fruits, and like for example, 3 tablespoons of vegetables is equivalent to 1 portion. So, data was converted and provided to the users, that is us, from the UK Data Health Survey. So, the major contributions of my paper is that I found a strong negative association between intake of fruits and self-assessed health, then various measures of blood pressure like mean arterial pressure, high mean arterial pressure, high blood pressure, systolic and diastolic BP, and your total cholesterol. Apart from that, I have found a strong positive association between consumption of vegetables and good cholesterol. So, it is recommended in a way that if you want to control your blood pressure, you must consume more and more fruits. And as far as vegetables are concerned, they impact your good cholesterol. Apart from that, I went in for a falsification test. A falsification test is basically conducted to know whether the model that you have adopted and the conclusions that you are drawing are not spurious. So, if a falsification test is done to know, in a way it is tested by seeing an indicator, a health indicator which is not being impacted by your consumption of fruits and vegetables, and then we see whether there is significant result or not. If there is no significant result, that means your model is good and your results are non-spurious. So what we did is, for falsification test, we took ear complaints and infectious diseases. Now ear complaints, like if you are deaf since birth or you have some kind of imbalance, body imbalance, that is not being impacted by your consumption of fruits and vegetables, and we did find insignificant results. Apart from that, infectious diseases like HIV, AIDS, etc., we found similar insignificant results, indicating that our results are non-spurious. Apart from that, we went, since there was a lot of heterogeneity in the data, like by gender, by age and by weight, we did the regression analysis. We found results which stated that as far as fruits are concerned, it impacts a male's health more than a female's health. So it is basically said a man should consume more fruits to impact his health, whereas as far as vegetables are concerned, they impact a woman's health more. But this has been only seen as far as cholesterol is concerned, the various measures of cholesterol like total cholesterol, good cholesterol and your incidence of getting high cholesterol. Now after this, we went in for a policy implication, and in the policy implication we tried to find two policy implications: what matters and exactly how much portion matters. So as far as how much portion matters, we have found that on an average 5 or more portions of fruits impact your overall health, that is your self-assessed health, your MAP, your incidence of high MAP and incidence of high BP. But if you want to have a good mental health, so you can optimize your mental health by consuming 3 or 4 portions of fruits as well. And similarly, as far as self-assessed health and total cholesterol is concerned, an individual must consume 4 to 5 portions to optimally have the impact of consumption of fruits. Apart from that, vegetables have had a very little impact on your health. It only impacts your incidence of getting high MAP and high BP, and it's seen that only it impacts when you consume 5 or more portions of fruits. So an optimum consumption of 5 or more portions of fruits and vegetables are recommended, but fruits have a more impact on your overall health on various measures like self-assessed health, mental health, your various measures of blood pressure and various cholesterol levels. Another thing that we find is which type of fruit matters. It has been seen that all size fruits, they impact your self-assessed health, your systolic and diastolic blood pressure, your mean arterial pressure, your high BP and incidence of getting high MAP and high cholesterol. But we find that as far as frozen fruits or canned fruits are concerned, they help in regulating your incidence of getting high MAP or high BP, but it has a trade-off. That means there is something negative happening. It reduces the good cholesterol in your body. Apart from this, if you have an incidence of getting high cholesterol, it is recommended that you must consume fruit juices because it has a impact in reducing your probability of getting high cholesterol. And dried fruits, they impact your self-assessed health. As far as vegetables are concerned, very little impact has been seen. It has only been seen in case of portion of salads and its association with self-assessed health. Another thing that they have seen is vegetables in composite, they have an association with good cholesterol. So overall, my research basically says that there is an association between consumption of fruits and vegetables and various health indicators, and it is highly recommended that an individual, in order to be healthy, must consume 5 or more portions of fruits and 5 or more portions of vegetables per day, but fruits have a more impact on your overall health. Apart from that, all size fruits, they have a better impact on your overall health, your mental health, various measures of blood pressure and cholesterol. So, thank you.